So, having seen what the thermal effects on a motor are, let us also pay some attention to the box behind the motor called the controller, which is driving the motor, which is called the motor driver or the motor controller. The controller also is primarily defined by the thermal limits. The challenge in the case of a controller is even more when designing compared to the challenge in the case of a motor, because the controller is usually designed by electronics engineers, motor is often designed by mechanical engineers, and electronics engineers understand nothing about thermal, it is not in their syllabus. So, very often they come up with the design and then they pass it on to a mechanical engineer and say, now you take care of the thermal. It is not possible to do that, because thermal is inherent to the design of the electronics, whether it be the circuit layout, whether it be the component selection, everything has to be informed by thermal considerations. So, usually when an electronics engineer designs a power electronics circuit, the result is disaster. It is a disaster because they have not paid attention to thermal. So, the idea of this lecture is to give you a quick overview of what are the important thermal considerations in electronic design, in particular in power electronic design, because that is where thermal becomes a significant challenge, and how to address them. And these have to be done at the design stage when the circuit layout is being designed, when the components are being selected. It is not an add-on that after you finish all the design you slap on a fin and then put a fan and keep it cool, it is not like that. So, the first, I will tell you about the limits. There are three important limits that we should keep in mind. The first is that the epoxy, which is the green material of which the PCB is made, often glass reinforced epoxy, it has a certain temperature limit which is called TG, the glass transition temperature. You should not allow the temperature of the PCB to rise beyond that during operation. The second important limit is that all the components are soldered on the PCB. The process of soldering itself involves melting the solder and placing it at the point where you want the component to be bonded, and after it cools it bonds strongly. Now, during operation, if the temperature at the solder goes above the melting point, then the solder will again melt and the component will come loose, which is not something that we want. So, this is the other temperature limit we have to keep in mind. And finally, all the semiconductors, as you are aware, the semiconductors are made of N and P junctions, and at these junctions there is an upper limit to which the temperature can be allowed, beyond which the component will fail, and that is called the junction temperature. And during operation of the electronic circuit, we should ensure that the junction temperature is always well within the limit prescribed by the manufacturer of the component. Usually that temperature is about 175 degrees. We should not allow the temperature to get anywhere near that. Now that we understand the temperature limits, what will happen if we do not take care of it? Components can blow up, like I told you about the semiconductors. This picture is of a MOSFET. The junction temperature breached the limit and the component blew up. Another thing that could happen is the traces. The traces are the copper tracks that you see on the PCB through which current is flowing. The traces are bonded with the epoxy and they could come off, and solder, as we already discussed, could melt, and therefore the components could come loose, and in extreme cases the whole thing may catch fire. because a lot of components are crowded in a very small space and enclosed with very little room for heat to go out, and it could lead to a fire accident. Many of you may have heard of some phones and laptops suddenly bursting and catching fire in flights, and they were banned from being carried in the flights. All of that comes from poor thermal design. So even very large companies make these mistakes. It's a very important area that we should be mindful of. So let us look at how we keep these things under control. What is called the trace, the track of copper on the PCB through which heavy current flows. It has to be wide enough so that it does not get hot. Why does it not get hot if it is wide? Nobody knows. At least usually the electronics designers do not have much idea. Please tell me. Very good. So when the area of the cross section of the trace is increased, the resistance is lesser, therefore less heat is generated. Excellent. Any other reason? So whenever we talk of thermal limit, we are talking about temperature. Temperature is the result of how much heat is generated minus how much heat is removed. If I am generating 100 units of heat and I am removing 75 units of heat, then the net addition of heat is 25, and that 25 will cause a certain temperature rise. For the same 100 units of heat added, if I also remove 100 units of heat, then the net addition of heat is 0, so there will be no temperature rise. That is what is called steady state. Steady state temperature means there is no further rise in temperature, and that no further rise in temperature happens not because heat is not generated, but as much heat is removed as is being generated. So it is a dynamic equilibrium between heat getting added and heat getting removed. And increasing the trace width, yes, it reduces the heat generated. It also increases the area of contact between the trace and the PCB on which it is sitting, and when the area increases, more heat gets removed also. Is that clear? So both ways it contributes to reducing the temperature rise. So we will see that in a little bit of detail. This is a typical PCB with power traces. All the thick ones you see are carrying heavy current, and the thickness of the trace, anybody has any idea how thick the trace will be? Visually I can say that this trace maybe here is about 10 or 12 mm wide. What is its thickness? Any idea how thick it is? None of you have designed the PCB boards. When you design a PCB board, you have to tell the manufacturer, specify to the manufacturer what the thickness should be. Any idea? Usually it is 35 microns. 35 microns means how small? 35 by 1000 millimeter, very, very small. And if you want it really thick, then you could make it 70 micron. Or in the extreme case, you can make it 105 micron. 105 micron is about 0.1 millimeter. The normal trace will be about 1/3 of 0.1 millimeter or 2/3 of 0.1 millimeter, not more. The thickness is very less. So let us look at how much heat is generated. The heat generated is I squared R, and as you are familiar, the resistance is rho into length by area. So, I can rewrite the equation like this. Now, this area A, I will write it as W into T. What is W and T? The width of the trace multiplied by the thickness, as you can see here. So, the product of W and T is the area, and the heat generated is I squared into rho L by W T. Now, how much heat is being removed is what I want to know, and I told you in steady state, when the temperature is not rising, not falling, the heat added must be equal to the heat that is removed, and the heat removed is H, which is just a constant. We have already seen what H is, heat transfer coefficient, or the interface conduction coefficient. Interface means when two objects are in contact, and that multiplied by the area available for conduction into the temperature difference between the two surfaces that are in contact, the junction temperature difference. Now, this area of conduction is W into L, where L is the length of the trace, which is actually perpendicular to the paper. So, if this is the length of the trace that we are considering, then W multiplied by L is the area which is in contact with the PCB, through which heat is getting removed. Now, if I just equate the heat generated with the heat that is being removed, then I will be able to easily find that the current that the trace can carry is directly proportional to W into square root of T. I will advise you all to figure it out for yourself. Just by comparing the two equations, you know that the current is proportional to W into square root of T. So, let us say I want to pass 100 amperes. I have got 35 microns thickness and a trace width of 10 millimeters. Supposing I make the trace thickness double, I make it 70 microns, then what will happen to the trace width? What will the trace width be? I have doubled the thickness of the trace. Before that, I found that a 10 millimeter wide trace was enough to carry the 100 amperes that I want. Now, I have doubled the thickness. That means I can reduce the trace width. What will be the new trace width? The equation is right here. If I double it, width will become 70%, width will not become half. If I only go by the heat generated and look at the area of cross section, then if I double the thickness, I will halve the width and make it 5 mm. But when I reduce the thickness to 5 mm, I am also reducing the area of contact by which heat is removed. So, actually temperature will rise. So, I cannot reduce it to 5 mm, I can only reduce it to 7 mm. If I triple the thickness, then the width can be reduced to 6 mm, not 3 mm. So, this is the interesting thing about it. Of course, practical engineers designing circuit boards do not understand this, but instead they follow some rule books with procedures and lookup tables, and they often get the design right. But it is always good to understand why the rules are there. It is not that we are blindly following some rules set by somebody, there is a logic behind it, and this is the logic. Then let me come to the second temperature limit, which is of the solder, and I will take the example of what is called a shunt. A shunt is a small resistance which is in the path of the heavy current that is flowing, and because it has a small resistance, when heavy current flows through the shunt, there is a voltage drop, and if I take a voltmeter and measure the voltage drop across the shunt, I can infer what current is flowing. So, a shunt is a way of measuring current by probing the voltage. The problem with the shunt is that it is a very tiny component, very small, and at the floor where you see here, at this place, it is in contact with the PCB on the two sides. That area is really small and it is soldered there. It is soldered onto the copper tracks. You can see the copper tracks here and the shunt is here, and between them what you see is the solder. That solder is holding the shunt onto the copper track, and a heavy current is flowing through it. Because a heavy current is flowing through it, it will get hot. If it gets too hot, the solder will melt and the component will come loose. We want to avoid that. There is a concept called heat flux, which is normally a very useful thing to understand how intense the heat is. Heat is measured in watts, but intensity of the heat is the watts divided by the area. Just like pressure is force divided by area. I can press you with my finger and you do not feel any pain, but if I hold a needle in my hand and press you with the same force, you will shriek with pain, because the same force is getting applied in a very small area. In the same way, it is not just the heat in watts that matters, but what is the area through which it is being transmitted. If the area through which the heat is being conducted is very small, then the heat is very intense, and that is called the heat flux. It can be measured in watts per centimeter squared, and 0.8 watt per centimeter squared is fairly high. It is a reasonably intense heat flux. Now you can see this little animation. There is a PCB, the shunts are shown. You can see the current flowing through the tracks, as a result of which the shunts get heated, and most of the heat will go through the copper tracks because it is a good conductor of heat. Some of it will also get convected into the air around, but the amount of convection is very small because air is not moving, it is still, and the entire thing is in an enclosed box. So we can neglect the convection for all practical purposes and just say that the heat will be conducted by the copper track. And we have to design the contact area and other things in such a way that temperature is within limits. Finally, we come to the semiconductor, where I said the junction temperature has to be kept within control. What you see here is a PCB. The semiconductors you see here are called the MOSFETs, metal oxide semiconductor field effect transistor. There is an expansion of it. Essentially, it is a transistor which switches on and off, and when it switches on and off, heavy current flows through it when it is on and does not flow when it is off. And internal to the MOSFET, there is a parameter called RDS on, resistance from the drain to the source when the switch is on. That is the resistance which acts when current is flowing, and that resistance contributes to heating up, and that heat can be very intense because the MOSFET itself is just 1 square centimeter, very small in area, and the side on the other side where you do not, which is not visible in this picture, is metallic, and that is the face through which the heat has to come out, and the area of that metal is just about 1 square centimeter, 1 centimeter by 1 centimeter, and all the heat inside should be quickly removed through that small area, and you can see that it is already 4 times as intense a heat flux as you saw in the case of a shunt. The shunt was 0.8 and this is 3.3, 4 times more, very intense heat through the semiconductor. But as we already discussed, the temperature rise depends not only on the heat generated, it depends upon what else does it depend upon? It depends upon the heat removal rate. If the removal rate is as fast as the generation rate, there is no further increase in temperature. So, how do you increase the heat removal rate is what we will be seeing in this little video. Again, there is a PCB, we have pasted something called thermal pads for better conduction and contact, and placed an aluminum block, and then on top of it we have a heat sink with many fins, and then when current starts flowing, you can see that the heat is being conducted through the metal block and coming onto the surface, and it is being carried away by the air, and depending upon how much heat is coming out from the fins, you can depend upon natural convection, or you may have to blow air and so on. So, that is it as far as this is concerned. If there are any questions, do ask. Anything else?